In this video, we are going to discuss on the various organic reactions involving aromatic compounds. Before I continue, I want to thank those of you who have subscribed to my channel. And for those of you who haven't subscribed, remember please that our major interest is seeing you succeeding in your exams. Our resources are free. What we want from you is just take a bit of your time, subscribe to our channel, like our videos, and share to learners who will be sitting for the same exam next year or in 2 years' time. Thank you for taking your time to subscribe to our channel. Let's get started. Aromatic synthetic roots. We will be starting with benzene. We will be starting with benzene here. But it should be remembered that benzene ring, benzene has a high density of electron-rich ring. There is high electron density in the ring, and benzene will not undergo addition reaction, electrophilic addition. But benzene will undergo electrophilic substitution in all its reactions. It will not undergo electrophilic addition, but it will undergo electrophilic substitution because of its high density of electrons in the ring. Now, we'll be starting with benzene, and the first reaction will be hydrogen. This first reaction here. This first reaction will be dealing with this hydrogenation, converting benzene to cyclohexane. Converting benzene to cyclohexane. Benzene to cyclohexane is this is by hydrogenation. This is by hydrogenation. In this case, the benzene will react with hydrogen. And we will need a nickel catalyst, a nickel or platinum catalyst. These are two catalysts. Either you use a nickel catalyst or you use a platinum catalyst, and you heat the reaction mixture. When you heat the reaction mixture, the outcome of it, or the product of the reaction, will be a cyclohexane. Cyclohexane. Let me just write it here for you to understand. We will have benzene here, like this is benzene. This is benzene plus yeah, it should be 3 hydrogen. Okay, it undergoes, we will have a cyclohexane, which is this one. A cyclohexane, or you can put it in this way. Another way you can put it there could be, you have a CH2, a CH2, a CH2, 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 yeah, that is what you have. Or a reaction condition will be a nickel catalyst, nickel catalyst or platinum catalysts. That's heating. We'll have that. This is a cyclohexane, called the cyclohexane. Cyclohexane, which is a C6H12. C6H12. That is a cyclohexane. That is a cyclohexane. But an alkyl benzene, such as for the purpose of revision, an alkyl benzene can still undergo this, but the addition will not, an alkyl benzene such as a methyl benzene can still undergo this. We'll have a thing like this. Methyl benzene will still undergo the same reaction. Something like this. Yeah. It will give us methyl benzene. Yeah. Yep. This is what we'll have. It will be cyclo. We can call it cyclo. You can call it a cyclomethyl benzene. Yeah, a cyclomethyl benzene. No cyclohexane. It will be cyclomethyl benzene. You can call this one cyclomethyl benzene. This one will be C6. The formula of this one is C6 H11, because one hydrogen has been substituted, H11, then with CH3. That is C6. We have that is C6H11 CH3, cyclomethyl benzene. So that is what you undergo using a nickel. We have a nickel or platinum catalyst. So by heating it, you can have that. So now that is by benzene to this. Then benzene to bromo. Benzene to bromobenzene to this bromobenzene here. The only thing you can do is by electrophilic substitution. It is by electrophilic substitution. So you can undergo it by electrophilic substitution. Let's see how we can do this. And we will have this. Okay. Okay. Let's see how we can produce. Let's see, how we can produce bromobenzene from this one, from benzene. How are we going to do this? How are we going to do this? We have the reagent in this case. The reagent in this case, we have bromine. We have the bromine, which is the reagent. We will also have iron 3 chloride, iron 3 bromide, or a halogen carrier. Let me just say a halogen carrier. There will be a halogen carrier there. You could use iron 3 bromide or aluminum 3 aluminum chloride. You could use aluminum chloride or iron 3 chloride, any of the halogen carrier, iron 3 chloride or the aluminum chloride. You can use any of them and you will produce it. Let me show you how you can do it. Of course, you could be asked to write the equation. Here, this is what we are going to get. This is what we are going to get here. We will have benzene. If you need the details of it, please watch our previous video on halogenation. So we will have this. We have that. This is what we are going to have. We will have this electrophilic substitution. Bromine is going to substitute the hydrogen, and this will be the product, the bromine here. Then plus hydrogen bromide. Once more for the reaction mechanism, watch our previous video on halogenation of benzene. Okay, this is how this is done. We will have anhydrous. This is anhydrous. Anhydrous anhydrous aluminum anhydrous aluminum chloride or iron 3 chloride, iron 3 bromide. Oh, sorry, let me use aluminum. Sorry. Anhydrous. I said you can use anhydrous. Anhydrous iron 3 bromide or anhydrous iron 3 bromide or aluminum bromide. You can either use this. This will be as catalysts. You can use anhydrous iron 3 bromide or aluminum chloride. All of them are halogen carriers. All of them are halogen carriers. The most important thing here is the how you can produce the electrophile. How an electrophile can be produced. Okay, this is how this is done. Look at the equation very well. The most important thing for the reaction mechanism is how you can produce the electrophile. We will have a bromine, production of the electrophile. This will be a bromine. This will be a bromine. This is a bromine molecule. The bromine molecule and the ion. Let me use the ion 3 now. Ion 3 bromide. Ion 3 bromide. Now an electrophile. See how the electrophile is being produced. The electrophile here is this one plus the complex ion this is what is happening there. I'm coming to explain how it goes. We have this a partial positive, a partial negative, then we will have from here that is what is going to happen there. Now what is going to happen here is this. This is the whole equation. This is the whole equation. Aluminum plus, benzene plus a molecule of bromine using the catalyst. The catalyst could be ion 3 bromide, or aluminum bromide catalyst. Then we will have the product. But the first thing is how is the electrophile generated? You should know that the ion 3 bromide that I'm using here, the ion 3 bromide will polarize this bond. It will polarize the chlorine, the bromine bond. It polarizes the bromine bond, thereby creating the electrophile. I say the ion 3 bromide will polarize the bromine bond, thereby creating the electrophile. How does it do this? It does this in the following ways. The first thing is that the bromine molecule forms a dative bond. The bromine molecule will form a dative bond with the ion 3 bromide. The bromine molecule will form a dative bond with the ion 3 bromide. By donating a lone pair of electrons from one of the bromine. This bromine will donate a lone pair of electrons. This bromine molecule forms a dative bond with the ion 3 bromide by donating a lone pair of electrons from this bromine, from one of the bromine atom into the empty 3d orbital in the ion. Remember, ion is a d block element. Remember, ion is a d block element. For that reason, the empty d block d subshells, and this bromine here, in order to form a dative bond, covalent bond with the ion 3 bromide, it will donate a lone pair of electrons into the empty 3d orbital in the ion. When it donates this electron into the empty 3d orbital in the ion, what happens? This helps to draw electrons. When this bromine donates, it helps to draw electrons from this other bromine. It draws electrons from this other bromine atom here, thereby making this bromine, when it draws electrons from this bromine here, it thereby making this bromine to be partially positive, to have a partial positive charge. And this creates an electrophile. Once more, the electrophile is generated by what? By bromine forming a dative covalent bond with the ion 3 bromide. And it only forms the dative covalent bond with the ion 3 bromide by one of the bromine donating a lone pair of electrons into the empty 3D orbital in the ion. And when it happens like that, it helps to draw electron from this other bromine atom that is left here. It helps to draw electron from this other bromine atom that is left here. This makes the bromine atom to be partially positive, or to have a partial positive charge, which now results in the bromine being an electrophile. This electrophile will now be attracted to the electron-rich benzene ring, and when it is attracted to the electron-rich benzene ring, since there is the localized pi electrons there, 2 electrons will be donated to the electrophile, thereby distorting the ring. At the end of the day, the hydrogen atom that is there will escape, thereby releasing the bonding electrons that it was having into the ring and restoring the ring. So that is how it is formed. The same way, if you were using the other, halogen carrier, such as aluminum bromide, this is the same thing that will happen. It will be the same thing. If you were to use aluminum bromide, this is the same thing that will happen. It will be bromine into bromine. That is aluminum bromide to give our electrophile, and the complex. And the complex here will be aluminum Er4 minus. So now, what is going to happen here is this is the same thing. What is going to happen here is the same thing. It's the same thing. What is going to happen here is that it is the same procedure, but for the fact that the bromine here, the bromine is going to form a dative covalent bond with aluminum bromide. It is going to form a dative covalent bond with aluminum bromide by donating a lone pair of electron from this bromine here, from one of the bromine here, which is this one, into an empty 3p orbital in the aluminum. Aluminum has an empty 3p orbital. The aluminum in this aluminum bromide has an empty 3p orbital. So the lone pair of electron is formed by this bromine donating a lone pair of electron into the empty 3p orbital of this aluminum here. When this happens, now electrons are drawn from this other bromine here towards this one, and making this bromine to have a partial positive charge that finally result in it being an electrophile. So that is just the procedure, and subsequently it is followed by the electrophile. It is followed by the electrophile being attracted to the electron-rich benzene ring. If you want more details, go to our channel. Now we will go to the second one. The second one is this one reacting with benzene, forming an alkyl benzene. That is chloroalkane and anhydrous aluminum chloride. Anhydrous aluminum chloride as a catalyst. Yes, we can use that. This is we call it alkylation. We call this alkylation. So that is the same way we call it alkylation of this aluminum chloride. So this is how this one can be formed. Let me just wipe. Okay, I can see this below. The way this one is formed is by we will have aluminum to form. Okay, this is ethyl benzene. Ethyl benzene. Now we usually use a halogenoalkane. We usually use a halogenoalkane and especially a chloroalkane. So in order to form this, for benzene to form this ethyl benzene, we will use a chloroalkane, and the chloroalkane in this case will be chloroethane. We will use a chloroethane. The catalyst, as you have seen, is anhydrous aluminum chloride. Anhydrous aluminum chloride, which is the catalyst. It is aluminum chloride because we are going to use. It is aluminum chloride because we are going to use chloroethane. If we were to use bromoethane, the carrier will be anhydrous aluminum bromide. But since we are using chloroethane to produce this one, our catalyst will be anhydrous aluminum chloride. So now let's use a hydrous aluminum chloride to produce our this thing. So in this reaction, we will react benzene. In this reaction, we will be reacting benzene. That is alkylation of benzene. We will react benzene. This is benzene. We will be reacting benzene plus chloroethane. Since it is an ethyl benzene, chloroethane, that will be CH2. That is CH3. CH3. Okay. CH2. Yeah, that is what we will have. Then our catalyst, since we are using a chloroalkane, in this case chloroethane, our halogen carrier is supposed to be aluminum, anhydrous aluminum chloride. But if it was supposed to be bromoethane, our catalyst will be aluminum, anhydrous aluminum bromide. So in this case, let's use aluminum chloride, aluminum chloride catalyst. Aluminum chloride catalyst, and what would be our product? Will be, it's an ethyl benzene. That will be CH2. The hydrogen is substituted, so now it will be, the hydrogen is substituted, now it will be CH2 CH3 plus the hydrogen that leaves from here will combine with this one, and it will be hydrogen chloride. will be hydrogen chloride. So that will be our product. That will be our product. But the most important thing in this reaction is how do you generate the electrophile? This is the electrophile. How do you generate it? This is how the electrophile is generated. Here we will have this compound that is being given here. It will be this one, CH3. This is CH3. CH3. Now, this is our aluminum chlorides. This is our aluminum chloride. Now, this is our product. This is our what is being generated here is this one is CH3 CH2 CH3 H2C. Yeah, that is CH2 H2C. That will be then plus aluminum Okay, this is what is happening here. What you see here is this. This is a partial positive. This is partial positive. And this is partial negative. Now, there is a lone pair of electron that is, there is a dative covalent bond that is formed between this and that. There is a movement of electron from this our electrophile is generated. This is our electrophile that is being generated. This is our electrophile here that is being generated. This is the electrophile. This is our electrophile that is being generated. We call this a carbocation. A carbocation. Now, what happened, as I told you, that in order to generate our electrophile, there is this bond here, the chloroethane, there will be a dative covalent bond between chlorine here. Chlorine will form a dative covalent bond with aluminum of the aluminum chloride. Chlorine will form a dative covalent bond between there will be a dative covalent bond between between chlorine and the aluminum. And this is done by what? The chlorine will donate a pair. It will donate a pair, a lone pair of electron. This chlorine will donate a lone pair of electron into this aluminum, into the 3p orbitals, of this aluminum. This chlorine will donate a pair of electron into the empty 3p orbital in aluminum. And when it does that, electrons in this carbon are drawn towards this chlorine. And when electrons in the carbon are drawn towards chlorine, because chlorine is donating a pair of electrons into the 3p orbital, in this place, empty 3p orbital in this place, what will happen is the carbon atom here will be the carbon atom here will be what? Will have a partial positive charge. This partial positive charge on the carbon atom makes the whole of this molecule here an electrophile. This is a carbocation. Is now going to act as an electrophile. That is how an electrophile is generated. This electrophile here is now attracted. The electrophile is then attracted, or is then attracted to the rich, to the electron, the localized benzene ring. Either you say the electrophile is then attracted to the rich electron benzene ring, or it attacks, this electrophilic attack on the rich benzene ring. And from there, the benzene ring will not donate a pair of electrons to it. A pair of electrons to it, thereby distorting the ring. And when it distorts the ring, hydrogen will have to leave as a hydrogen ion. And the bonding electron between hydrogen and the carbon will be returned to the ring to complete the ring and restore it. And this would now form, and a complete bond would be formed between these carbocation and the benzene ring, giving ethyl benzene, the compound. So that is how the product is, that is how it is generated. Secondly, we will have to move to the second one would be how benzene undergoes nitrobenzene is being formed. Nitrobenzene is formed from the concentration. Nitrobenzene is formed from reacting concentrated nitric acid and the concentrated sulfuric acid. The reaction between concentrated nitric acid and concentrated sulfuric acid generates what we call a nitronium ion. A nitronium ion. That nitronium ion is what we call the electrophile. The electrophile, that is what we call the electrophile. So the pair now, the electrophile is now, the nitronium ion, which is the electrophile, is now attracted to the rich benzene ring. Now, a pair of electrons in the rich benzene ring is donated to the nitrogen of the nitronium ion. And when it is donated like that, the ring is distorted, the ring is broken. The hydrogen ion there will escape, and the bonding electron that were existing between hydrogen and the carbon will return to the ring, will return to complete the ring, thereby restoring the ring. And by doing that, nitrobenzene will be the product. Let me just show you how it happens. Now we have, the reaction is this one. This is the reaction. Okay. This is a reflux. So that is a. It is reflux. The reaction mixture is reflux at the temperature of 25 degrees Celsius to 60 degrees Celsius, and the outcome will be nitrobenzene. The outcome will be nitrobenzene and plus a hydrogen ion. The hydrogen ion will not be picked by the will be picked by the HSO4 to form the sulfuric acid again. So how do we generate the nitronium ion is our question. This is how nitronium ion is generated. We said this is nitric acid. This is nitric acid. We have this H2SO4, H2SO4 to give NO2 plus 2H SO4 minus and plus hydronium ion H3O plus. This is our electrophile. This is our electrophile that is being generated. That as I told you that, see what is happening. We will have this. We will have this. We will have this. We will have this. And then finally we will have this. And plus this. This one is now picked up. This one will be picked up by the HSO4 minus. This one will be picked up by the HSO4 minus to form the sulfuric acid again. And see the mechanism. I said go back and you have the details of it. You will see this and you will see this. What is happening there? I told you that the nitronium ion that is being produced is attracted to the electron-rich center here, the electron-rich benzene ring. And when it is attracted there, because they have the localized pi electrons in here, two of the electrons, a pair of electrons is donated to this nitrogen here. A pair of electrons is donated from the ring to this nitrogen of the nitronium ion. And now this is a pair of electrons that will be donated here to form the bond here. Now, when it does that, the ring is distorted, the ring is broken. Now hydrogen will escape as a hydrogen ion, and the bonding electron between the carbon here and the nitrogen will return to the ring to complete the ring, and restore it. Therefore, nitronium ion is formed and hydrogen ion is left here. The nitrogen ion is picked up by this HSO4. So this is how you get it. Thank you. Let's go to the fourth one. The fourth one is, let me clear the board. Okay. Okay, let's go to the next one. The next one is now let's go to the nitronium, the nitrobenzene. Nitrobenzene again it should be noted that the nitrobenzene, it should be noted that the nitrobenzene, which is this one here, the nitrobenzene here will do what? It will react, nitrobenzene will react with tin and hydrochloric acid, and this is reduction to produce phenylamine. To produce phenylamine. I say phenylamine, this phenylamine is produced or it is formed by the process of reduction. Phenylamine is formed by the process of reduction. I told you that reduction, by the process of reduction, during the reduction, there is addition of hydrogen to the compound. During reduction, we add hydrogen to the compound. So now during a reduction, we are going to use the reagent here. The reagent here, we will have concentrated hydrochloric acid. We will have concentrated hydrochloric acid, and we will also have tin. This concentrated hydrochloric acid will also have tin. This is by reduction. And the reaction condition here is that this reaction mixture, concentrated hydrochloric acid and tin and nitrobenzene, all we heat them under reflux. We will heat them under reflux. We will heat this reaction mixture, tin and concentrated hydrochloric acid with nitrobenzene under reflux. And when we do that, we will have our nitro, we'll have our phenylamine. We'll have our phenylamine. That is what is happening. So I said this is, you can see it here. Let me just write the equation for you to see what is going on. So this is our reaction. This is our reaction. Our reaction here is this one. We will have this, the nitrobenzene plus hydrogen. I said it is a reduction. Reduction has to do with addition of hydrogen. Meanwhile, in oxidation is addition of oxygen. So addition of oxygen. Now we are passing it through what? There is HCl, concentrated HCl, and concentrated HCl and tin, then under reflux. Under reflux, and what you will have is phenylamine. It is the phenylamine. The phenylamine is what you will get. Phenylamine is what you will get. Phenylamine is what you will get. Plus 2 molecules of water. And if we do that, we are going to add this to be what? We are going to add it to be 6. Yeah, to be 6. So this is phenylamine. Phenylamine. That is what we are going to produce. That is phenylamine. That is the phenylamine we produce from here by reacting benzene, by reacting nitrobenzene, and with tin and concentrated sulfuric acid, concentrated hydrochloric acid. Sorry. And this process is by reduction. So when we have phenylamine, remember that the phenylamine, we can now, there can be what we call nucleophilic substitution. There can be what we call nucleophilic substitution by substituting one of the hydrogen here. By substituting one of the hydrogen here, we will now do what is with chloromethane. It will undergo substitution reaction. Now again, the phenylamine again can react with an acid chloride. or ethanoyl chloride. Ethanoyl chloride, you can react with the ethanoyl chloride again. The reaction is not going to be taking place in the ring, but it is taking place within the amine group. It is the reaction is within the amine group. It is substituting one of the hydrogen in the amine group. It is substituting one of the hydrogen in the amine group. It is not taking place in the ring. So any of these reactions here is not taking place in the ring, but it is the side reaction. The reaction is taking place, but within the amine group. Here, the chloromethane, one of the hydrogen was substituted. With the ethanoyl chloride, one of the hydrogen was also substituted. So that is what is happening. Then on the other hand, it can react. There is a reaction to form what we call a reaction of diazotization. There is a diazotization reaction where the phenylamine will react. The phenylamine will react with nitrous, with sodium nitrite and hydrochloric acid at a temperature of less than 10 degrees Celsius. And when that happens, it forms a diazonium salt. And when a diazonium salt, this is diazotization to form the diazonium salt. So this is what is happening. The phenylamine will react with this to form this phenylamine with this one here, a temperature of less than this. Initially, this is sodium. This is what is happening here. Remember that the phenylamine is going to react with this sodium nitrate or hydrochloric acid at a temperature less than this. Let me show you the chain reaction, how it's going to work. So when sodium nitrate react with hydrochloric acid, there is the production of H nitrous acid, HNO2 plus sodium chloride. The sodium chloride. What we are going to use here is this HNO2. Is this HNO2 that we are going to use. Now, this HNO2, what will happen is it will react. It is going to react now. The phenylamine is going to react now with this reagent. The phenylamine NH2. The phenylamine plus this reagent, H NO2 plus HCl. What will be the result? When it reacts like this, a salt is formed, a diazonium salt is formed, a benzene diazonium salt is formed. This is the salt. That is the salt. The salt will be this one. A benzene diazonium salt is formed. which is N, 1, 2, 3 bonds with another hydrogen, I mean a nitrogen, then a chloride. Yes, we have this as a salt plus, and we have chloride here. So this salt plus 2 molecules of water, I can say plus 2 molecules of water. So this is the salt that is being formed. We call this a benzene diazonium salt. Benzene diazonium. Or benzene diazonium salt, or benzonium. Check. Benzene diazonium. Check there. If it is not there, you tell me. I will ask you. Benzene diazonium chloride. There's too much on here. You just check there. Call it benzene diazonium chloride. The benzene diazonium chloride, or you can call it benzene diazonium salt. This salt is very, very unstable. So this salt again, from the equation here, this is the salt. The benzene diazonium salt or ion reacts with an alkaline solution of phenol. An alkaline solution of phenol. When it reacts with an alkaline solution of phenol, we will have what we call an azole dye. An azole dye. Let me just show how it can react with alkaline solution of phenol. So here, this is what happened. This is what is happening here. This is what is happening here. We will have this salt here. In this salt, we are going to have. Let me represent the salt in this way for you to understand it better. This is the salt here. We have the benzene ring here. That's the benzene ring. That's salt. 1, 2, 3. Yeah. The chloride. From this chloride, I said there is a positive charge here, and there's a negative charge here. This chloride, I said it will react. This ion or the benzene diazonium chloride or ion will react with an alkaline solution of phenol in a coupling reaction. We call it coupling reaction. So this how it is the alkaline solution of phenol. This is how it will appear. This is how it's going to appear. Okay. Coupling. This is hydrogen. This is a phenol. That is a phenol. When this this is coupling, it said This is an alkaline solution of phenol in a coupling reaction. This coupling reaction, see what is really going on there. Let me see what is going on. A coupling reaction. Here, one of these bonds is taken to the chlorine. That is one of these bonds is taken there. Now our product here will now be the benzene. That is the benzene. Yeah. Yes. This hydrogen is removed. This chlorine and this hydrogen will form hydrogen chloride. This chlorine and this will form hydrogen chloride. And now it leaves to what? So that is plus hydrogen chloride plus hydrogen chloride. That is plus the hydrogen chloride gas. The hydrogen chloride gas that is released. The hydrogen chloride gas that is released. Oh. Okay. Plus the hydrogen chloride gas that is released. We can call this compound an azodide. We can call this compound, the whole of this compound, we can call this an azodide. And this is an orange precipitate. Precipitate. This is an orange precipitate. You can have that. So that is how you can produce this compound from here. From this compound here, reacting here less than 10 degrees. Then the salt is formed. The salt is from the ion. This ion, the diazonium. The diazonium ion reacts with an alkaline phenol, alkaline solution of phenol. The diazonium ion reacts with an alkaline solution of phenol in a coupling reaction. Here is the diazonium ion. This is the diazonium ion reacting in an alkaline solution of phenol. This is phenol in an alkaline solution. This is phenol in an alkaline solution. So the diazonium salt or the diazonium ion reacts with an alkaline solution of phenol to produce this azodide, and this has an orange precipitate. So you can still do it in this way. Instead of putting this reaction here, you write the reaction and you will have this. This now will be reacted and you will have the salt. You have the salt. That is salt. Benzene diazonium salt. The diazonium salt now is now reacted with what? With alkaline. It is now reacted with an alkaline solution. Alkaline solution of phenol. Alkaline solution of phenol. This reaction here, we call it a coupling reaction. A coupling reaction. Where the hydrogen chloride is now being produced. We will have an azodide that is being produced and hydrogen chloride gas. So let's go to another section of Okay, now we can again, okay, um, phenylamine. How does it react with phenylamine? How does it react with bromine? Okay, phenylamine with bromine has 2, 3, 4, 5, 6, 7 positions. Okay, phenylamine with bromine. Let me show you some reaction with phenylamine with bromine. Let me just write one here. Phenylamine. This is phenylamine. Yes. Phenylamine plus bromine. In our last video or previous lecture, I told you that the amine group, the OH group, and the alkyl group, any alkyl group, be it let me say a CH3, any other one, or ethyl group, OH group, and the amine group, any of this group, all of them, the alkyl group, the OH group, the amine group, all these are electron donating. They are all electron donating. All of them are electron donating. And as they are electron donating, all of them are electron donating. So what happened is that for this group, as an electron donating group, what happened? It is an electron donating group. It has a positive inductive effect on the ring. So being an electron donating group, this is what is happening. Being an electron donating group into the ring, it increases the electron density in the delocalized benzene ring. So these groups, the amine group, the OH group, or the alkyl group, as they are electron donating, they are 2, 4, 6 directing. Why do I say they are 2, 4, 6 directing? They donate electron into the ring, and specifically to the position, to the 2 position, to this position here, to this position here, to this position here, and to this position here. So as they donate electron, they activate the ring at this position. They activate the ring by donating electron to the ring, increasing the electron density at the 2 position, at the 4th position, and at the 6th position. When the electron density at these 2, 4, 6 positions are high, it gives that ability for electrophile to attack the delocalized benzene ring at the 2nd, the 4th, and at the 6th position. So that is what is happening here. That is what is happening here. So they will, generally I say, these are electron donating, increasing the electron density at the 2, 4, and 6 position, enabling electrophilic attack at the position 2, 4, 6. So by doing this, they are activating the ring for electrophilic attack. So when they react with bromine, bromine is going to be substituted, it's going to substitute hydrogen. It's going to substitute hydrogen at the 2nd, at the 3rd, at the 2nd, at the 4th, and at the 6th position. Bromine is considered as the incoming group. So now, what would be the result? What would be the result of this? The result of this will be the methyl will have this as this one. We will have this. We will have this. And we will have this. our this is our bromine. This is our bromine, and this is our bromine. So it now results, then there are 3 bromines. So plus the 3 hydrogen that have been substituted will go out. So now they will form what we call hydrogen plus hydrogen bromide. Since there are 3 hydrogens here, I will put a 3 there. There are 3 hydrogen here. I will put 3 hydrogen have been substituted from the ring. So, and there are 3 here. So there are 3 hydrogens here. Then with 3 bromine, 3 hydrogen plus 3 bromine. Then with the other 3 bromine, making a total of how many bromine here? 3 bromine here. So how many bromine have been used? 3 plus 3 altogether 6. So that is how the equation is supposed to be, look like. And the product of this will be what? We will call it 2, 4, 6 tri bromo phenyl almine. Again, we'll call it 2,4,6 tribromophenolamine. So that will be our product. So that is how the reaction will go for the phenylamine at this position. So now we have done formation of the azo dye, the formation of the azo dye here. So once more, I said the phenylamine, when it reacts with bromine, phenylamine, the amine group is electron donating. It increases electron density at the 2nd, the 4th, and the 6th position. Therefore, the incoming group, like the bromine, will substitute hydrogen at the 2nd, at the 4th, and at the 6th position, giving us giving us 2,4,6 tribromophenylamine. Now reacting this here is just the substitution of the hydrogen there. Now reacting phenylamine again, I say we can react phenylamine with sodium nitrite when we had a nitrous acid, and the nitrous acid was reacted with phenylamine to produce the sodium chloride. To produce benzene disonium chloride. We have to produce the benzene disonium chloride. When we reacted it, we had that one to produce benzene disonium chloride. The benzene disonium chloride, the salt, can now react with alkaline solution of phenol, that is phenol in an alkaline solution. And when it reacts, like in this case, this is a coupling reaction. When it reacts phenol in an alkaline solution, when it reacts with this benzene disonium chloride, what will be formed will be an azo dye with hydrogen chloride that will be released as a gas. Now, another reaction in this synthetic pathway, which we have not visited, is we have done again for nitration. I said nitration, you can only get nitration by reacting. I said about nitration, you can get nitration. Nitration can be got by reacting concentrated sulfuric acid and nitric acid, concentrated sulfuric acid and nitric acid. When you do that, you have a nitronium ion. The nitronium ion will attack the benzene electron-rich benzene ring, and the electron will be donated to the nitronium ion and distortion in the ring. And they will be followed by hydrogen escaping and a hydrogen ion, and the bonding electron of hydrogen will be sent to the ring to replace, to complete the ring again and restore the ring. and the nitrobenzene will be our product. That's why I said it will be formed. And I also said that nitronium, and I also said that phenylamine can be formed by reacting uh, uh, by reacting nitrobenzene with tin and concentrated sulfuric acid, and this is by reduction. And this reaction mixture is heated in a reflux system. That was what I also mentioned. And then we also talked of alkylation of benzene using chloroalkane. Our example for this case was chloroethane, where I showed you how the most important thing is how you can obtain the electrophile. The electrophile can now go attacking the ring and formation of the ethyl benzene. So those are very, very important stages. Then I also showed you about reaction of benzene, that's hydrogenation, using a nickel catalyst, and that is being heated, and you will form a cyclohexane. And that can also be done using an alkyl benzene like methyl benzene. You can hydrogenate it using nickel catalyst or platinum catalyst, and we will have, as I told you, we will have the product that I showed you the other time. It will be cyclomethyl benzene, which I also showed you. And that is all I have for you. Thank you very much. You can revise this synthetic pathway. When you revise this synthetic pathway, you will have more of what I have been talking of. Thank you very much. Thank you very much. Thank you. Thank you. Thank you. Thank you. For those of you who haven't subscribed to the channel, please take your time and subscribe to this channel. Take your time and subscribe to the channel. You know, our main goal is for you to succeed in your exam. Subscribe to our channel, like our videos, and share to other learners who will be sitting for the exam next year or in 2 years' time. Thank you once more for watching.